Your voice will not come. So yeah. Okay. So just tell me the name of the workshop because I forgot. Right? No, that's right. Yeah, that's okay. The name of the title. Okay, number theory in algebra. Right. Okay. Mhm. Okay. Convergence of a sequence of matrices. It could mean many things. What do you think? So if you have a sequence of matrices A1, A2, dot 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 dot, and they are all in some M and K. Yeah. So then, okay, matrix norm. So you're defining the matrix norm. So this is defined for a matrix. Okay. So that's right. So are you going to so L1 norm I know operator norm is fine. Okay. So maybe you can just tell me maybe what do you mean by so let's see. So A in let's say square matrix or any matrix is fine, right? So, so maybe I'll just write M cross N matrix. Then you want to say L1 norm. Okay, so what is the L1 norm? Right, but then you were saying something about functions. Okay, right. Yeah, right. A matrix norm is just a norm. So yeah, so it satisfies the norm properties. Okay, and then there is operator norm. So what is that? Okay, maximum. Okay, okay. Yeah, but that's fine because these are so. I mean, you can prove it, I suppose, but these are norms on a finite dimensional vector space, so they are equivalent. Yeah, I mean that is the result which we have done. So yeah. Okay, let's wait. So exponential of a matrix, e to the a, is it just by the series definition? Okay, so then it's fine. Yeah, maybe I'll just write it because, yeah. So you have this, uh, okay. Yes, it converges. Wait, it is absolutely convergent. What does uniformly convergent mean in this case? Because see, when you say uniformly convergent, then it has to be a sequence of functions, right? And this is a sequence of constant functions, if you want to call it functions, right? I mean, because it's not a function, it's just a constant sequence, right? So it is uniformly convergent because it's convergent. Mhm. Okay. I have a question. So, when you say uniform convergence, on what domain are you asking? That you need to say. Otherwise, uniform convergence doesn't make sense. I mean, yeah, because okay, let's see. So, uniformly convergent. So, e to the x, right? Fx equals to e to the x. So, if you look at the corresponding series, is that uniformly convergent on R? No, right? Is fnx equal to, so x to the I by I factorial, right? Is this, so you should just take the one variable case, right? Uniform, because you are asking, you are trying to figure out how to, on what domain should you ask for uniform convergence, right? So is this uniformly convergent on R? Answer is no, of course. Yeah, is there, do you see that? I mean, if you don't see, then just say yes. So it's just because if you take fnx, just take fx minus fnx, then this will be equal to what? X to the n by n factorial and so on, right? Yeah. But this thing is not, so given any n, you can choose a x so that this is bigger than 1. So it's not uniformly convergent, right? Right? Because you have to make it less than epsilon. So given epsilon, you have to find the n so that this is less than epsilon for every x. But that you cannot do. So of course this is not uniformly convergent. Right? Yeah. So where should you ask for uniform convergence? That you should think about. Maybe later you tell me next time. Okay. Or maybe I can just I can tell you and then you can just you can prove it. So on any bounded set, this one will be uniformly convergent on any bounded set. You can just write it and prove it later. Because actually I'm not saying anything. I mean it is just that power series, a radius of convergence and blah blah. You know all that. So it just follows from there. And it's a completely one variable case. Say whatever you do, you just generalize it directly. So that's okay, but then what do you do with exponential of a matrix? Yes, but yes, so this infinite series, okay, so what is the corresponding sequence? The corresponding sequence is f and a. So you are saying that this sequence uniformly converges. Yes, but this is a constant sequence. The a is fixed, right? Or so if a is fixed and if you say that it is uniformly convergent, then are you saying anything? No, because it is convergent, right? So then convergence and uniform convergence is same thing. No, is it not? It is the same thing. Okay, that I do not know. That I'm that you should. Okay, I know the M test. That's fine. Yes, and it doesn't depend on A. But how? But okay. But how do you do that? Tell me when A is a one by one matrix. Means it's just a number. In that case, how do you do? What norm will you put? Okay. All right. So how do you make this number less than some constant? Oh, you cannot make it, right? How can you make it less than some constant which doesn't depend on x? Yeah, sure. Triangle inequality holds. Yes. So yeah, I mean x is just a positive number. Let's say. Then I mean, but how do you make it less than m? Let's say x is just a positive number. But how do you make it less than m? That is not possible unless you say something about x. Just think for a few and then see. Hmm. Right. Yes. Apply norm on this one. Okay. Right. Norm is not multiplicative though, in general. But yeah, you are using sub-multiplicative. Yes. It is still true, but it's not multiplicative, you said. Yeah. Okay, then. Why? Okay, yeah, so for bounded matrices, it is true. Huh. Yes, yes, that's what I said. Right. But we said that if A is in bounded, then it's uniformly convergent. And you are using the Weierstrass M test or any test you use to show that's up to you. Yeah. But it is, yeah. So that's what I mean. So when I asked here, I mean, is this true? This is not true for all x. Of course, it is true for bounded x that every, I mean, no, then this is just a generalization of that. Yes, that's all right. But then what do you do after defining the exponentiation? Okay. Yes. Yes. So if you take, yeah, I understand that. So you take this x going to e to the x, and you want to say that its partial derivatives are uniformly converge. Uh, yeah. So you want to say that the partial derivatives are also convergent. Okay. So partial derivative of the yes, yes. I mean that's what I mean when I say partial derivative is convergent. It because it's a series, so its partial sums are convergent. That's what it means. Okay, that's fine. Let's assume that it happens. It's not a big deal. Yeah. T times of A. Why do you need T? Okay, so you are considering a slightly different function maybe. So you're taking R to Mn R and you're taking T to e to the this function. Okay, so this is because now you are going to one variable case, right? Why not find this? Why not find the derivative of that? You can, but anyways, but you should tell me what you have done. So yeah, so you want to take this function. What name should I give? So which function do you want to take? The first one or the second one? Second one. Okay. And what name do you want? Do you want to give any name or you want to take DDT? So what is DDT of this? Uh, T T or A? Oh, okay. It's T. Okay, cool. You're saying that this, how can it be T? That's okay. Okay, it is this. Then, okay, fine. You can prove this somehow. Fine. Then what? Uh, so if the Lie bracket is 0, you can say like that. Okay. Then, right. This is all nice. Okay. This is also fine. You can prove it. Okay. Uh, uh, that I don't know. So subsets of GL and R. What are all the closed subsets of GL and R? Yes. Okay. Means you can prove all these things, right? Okay. Yeah. Okay. Yeah, that is one closed subset. I can give you examples of many closed subsets, but you cannot find all closed subsets, I think. Yeah. Okay, then what do you do? Okay, so you want to define tangent space. Okay. Tangent space of what? GLN. Any subset? Of Mn of R. Okay, of any but okay, fine. Any subset of Mn of R. Okay. Okay. Hmm. So okay, so I'm taking, so is G is equal to Mn R? Okay, right, tangent space. Right, a path in MNR. Yes. Hmm. Uh, right, gamma is a continuous path, and gamma of 0 is equal to I, and gamma is well, you need it to be differentiable also because you're taking derivative. So, okay. I is not. Oh yeah, both of these are same. Okay, so it should not be like that. Okay. So it is some, but it's fine. We understand it. I mean, just call it in. And so, what should I put here? What should be the domain? Yeah. Okay. So this is your definition of tangent space. Okay. Yes, that's fine. Yeah. Under addition. Right. So x comma y. So should I say gamma 1 comma gamma 2? Matrix. Wait. So I'm a little confused. Uh, okay, yeah, I'm sorry. Yeah, so you're saying that this gamma prime 0 is the matrix. Of course. So this is a, uh, yeah. So why is gamma prime 0 a matrix? So that's fine. Okay. So then, yeah. So x comma y is in TIG. It implies that the Lie bracket. So how do you prove this? Right. Right. Hmm. So what is that path? Does this path work? Yes, this one works, right? Yeah, so we just take the derivative. Okay, but I think I am doing something. Yeah. Yeah, the problem with this path is there is a problem, right? It is, that's the problem. So it's not identity, it's x minus y. So this one, and it should, yeah. So this is bad. Yes. See, Vaishnavi, so the point here is that, I mean, in this case, it is very simple because it is this G is equal to M and R, right? G is equal to M and R. So this is true because, I mean, any A in M and R, yeah, uh, is in TIG. And TIG is equal to M and R. Yes, that's right. In that case, it's not. So it's one has to think. So let's think. So maybe I should also write GL and R, and then we can. Yes, right. So the tangent space is M and R. So then also it is. Then also this will be true. Yeah. So so can we just separately prove that the tangent space is M and R? Let's see. Tangent space of GL and R is equal to M and R. Look, if you can prove this, then this is done. Although I would say, of course, that's not a good way to do this, but yeah, but then it is done. So let's see, tangent space of GL and R is M and R. Yeah, so you have to just use the previous thing, this one, right? Is that right? So given A in M and R, what curve should I take? Yeah, that's what, right? Yeah, TA. So that's why that exercise, that's why you did that. So that's for this. Yes. Okay. So then it is, then this is done, right? So what should be the good question to ask? I don't know. How do you prove this? Hmm? Tangent space of SL and of R. Do you know? You don't know? Yeah, SL and R, I don't know. I know for O and R. For SL and R, I don't know. Yeah, maybe we should do that now. Determinant something, right? I agree. But uh, yeah. Anyways, so this is one question to answer. So we should think about this one. And but before that, mhm, A is e power trace A, right? I know that. Is that correct? Okay, yeah. Determinant of e power A is e power trace A. That's you can prove that. I'll leave that for you to prove. Yeah. Yeah. So what I was saying is we should so how do you make this question better? Means better in the sense that in the following sense. So do you know manifold definition? Well, you should know, you should read it because if you're talking about the tangent space, you should know what is a manifold. Otherwise, how do you talk about tangent? Because tangent space doesn't exist for any subset, right? Tangent space doesn't exist for any subset. If you just take any subset, or maybe we will see. So let's see. Yeah, so tangent space of any subset of M and R, right? Any subset S, let's say, any subset S in M and R, right? This. So here, if you write S, or maybe I'll call it M because maybe it will make it a manifold and then we will talk. Right. Sorry. Closed subset of R power n Cantor set should not be a manifold. I, I suppose. Right. So any closed subset is not a manifold. So a manifold is, yeah, actually it is a subset of R power something, but that's a big theorem. That's a theorem. It's called Whitney's embedding theorem. But long before that, first we learn the definition of a manifold. So manifold is, so here we are talking about smooth manifolds. Okay, because yeah, sorry, here you're talking about topological manifolds. Okay, so what is a topological manifold? It is a topological space. Okay, it is second countable Hausdorff. Okay, and given any point x, there is a neighborhood which is homeomorphic to Rn. Okay, so given any point, there is a neighborhood which is homeomorphic to Rn. So this is the definition of a manifold, and this kind of thing can be said about any manifold. Okay, and tangent space is defined for manifold only. For any subset, of course, you have defined it, so you can define it, but it may not have good properties. Okay, so for example, this Lie bracket thing, I don't know if it is if this will be true, but let's just think about this thing first. Okay, and how do you show that the Lie bracket is also inside? Okay, and then we will try to compute the tangent space of SLR. That's fine. And also, I mean, you right, no, this definition is fine. Okay, sorry. So let us just think why this will work. I mean, so I know a proof, but that first builds an equivalence with this definition and some other definition. Okay. And then through that definition it follows very easily that the Lie bracket is that the tangent space is closed under Lie bracket. Yeah. But but directly we need to see. Hmm. Yes. Ah, yes. Say. Hmm. Okay. Okay. Hmm. Into no minus. Comma 1s inverse. This like this inverse. But why should that exist? Okay. Yeah, I don't know. But it need not exist, right? So need not exist. But okay, I mean, what are you planning to do with this? Suppose it exists. So let's say that G is a group. So it's a subgroup of GL and R. Then it exists. Then what? But then what do you do? Hmm. Hmm. Right. Then you get Y, and you get this thing. So Okay, in the product only, not separately. That doesn't sound very good. Then it just becomes like this, right? Okay, yeah. So then the S is some. What is the role of S? S is fixed. Okay, okay. S is fixed. Then how are you going to get this derivative to be this? No, no, that does not work. This definition with this definition, it seems a little tricky. I'm not able to do it. Okay, not able to do it with this definition. However, I'll tell you a different definition, and using that we will do. Is that fine? And of course, I mean, I'll show that they're equivalent. Okay, and but you should think about how to do this directly, right? So let's, yeah. Hmm. But you know that so it was done, but yeah. Uh, Anyways, so you can think about the path and you can tell me, okay, right? But I'll tell you a different definition. So uh, right. So what I'm going to say is, let M be a manifold, and of course, so you can take M to be a subgroup of G of M and R. Okay, okay. So subgroup of M and R. Fine. Or actually, as you were saying, closed subgroups of MNR you can take. Okay, they are all Lie groups, and Lie groups are manifolds. Yeah, but what I'm saying will work for any manifold, and there are manifolds which are not Lie groups. Okay, so but you should. if you know the definition of manifold and all, then it's a good thing. So you should learn that. But anyways, M be a manifold. Uh, so there has to be a smooth structure. Yeah, so we will need a smooth manifold, but also you can keep the same example as closed subgroups of M and R, like GL and R, SL and R, and so on. Okay, so I'm going to take a smooth manifold, and then you have two definitions of tangent space. You fix an arbitrary point P, so fix P in M, okay, then your TPM, TPM in terms, oh yeah, actually uh, I don't actually need smooth manifold. I will do it directly. So what I will define it is like this. You just take gamma such that such that such that gamma 0 is equal to P, and gamma is is from is like this, but I will quotient it by a relation, and the relation is gamma 1 is equal to gamma 2 if uh, um, gamma 1 uh, restricted to some some interval is equal to gamma 2 restricted to some interval. Is this fine? Okay. You see why I'm doing this? Because I'm not able to take the derivative because I'm not in a smooth manifold. Okay. In general, so I'm not able to take the derivative, but you will be in a smooth manifold. If you're taking closed subgroups, they will be smooth. So you can do differentiation, but in general, you don't know if you can actually do differentiation, right? So you were putting here the gamma prime of 0, right? I'm just putting gamma because I cannot take gamma prime 0. But then I'm taking this relation because you know that if two things have the same derivative at 0, then this should be true. Right. So that's why this relation is there. So this is there. So this is the definition of this is the my definition one definition of tangent space. And there is another definition of tangent space, and that is uh, in terms of derivations. So I'll tell you what this is. So this is basically we'll use the notation D maybe D, uh, right? So D, and what is D? So D is going to be uh, D is the collection. D is a map from uh, this to R, and this is all continuous functions on the manifold. Okay, it's a collection of continuous functions on the manifold, and I'm taking the dual of that. Okay, with the property that D is linear. D is linear, so it's actually a dual. It's actually in the dual space of CM. Okay, and also you want this Leibniz type of property to hold. So D of Fg is equal to F is equal to wait, since the point is equal to P, yeah, right, so that's okay. So is equal to df times gp plus plus uh, fp times dg. Okay, so this is another definition. Okay, now, so the first definition made intuitive sense to you, but what about the second definition? Uh, so this definition is like this. You um, so tangent space is supposed to be directions, right? So you are in a manifold, and now you want to take some direction, right? You want to talk about a direction. Now see, whenever you have a direction, what do you do with the direction? You take directional derivatives, right? So whenever you have a direction, you take directional derivative. Now if now this dv stands for directional derivative, then what does the directional derivative do? It obviously takes a continuous function, I mean directional derivative at the point, right? It will take a continuous function and return the directional derivative of f at p. Is that right? And this will be a real number, right? Because so it will be a real number. So it will be linear, and you also know that directional derivative satisfies this property. Okay. So you see, so every direction is a directional derivative, right? And directional derivative you can say without the term direction. Because these are the properties of a directional derivative. It is a map from continuous functions to R. I mean, directional derivative at a point. It has this property, it has this property, it has this property. So we just write these properties. We don't write vector v because we don't have that notion. We are trying to define that notion indirectly. Fine. So this is the other. This is a very wise definition, of course. Yeah. Right. And now we want to say that these two definitions are the same. Right. So definitions are equivalent. So let me give you a rough picture of why they are equivalent, and then maybe we will see. Or yeah, just wait. Okay, yeah, let's try to see that. So yeah, so let's say that let's say d1 and d2 are in the tangent space. Okay, then you want to take the Lie bracket, that will be this, right? But I mean, the first question is why is this even how is this even a function from CM to R? That you need to first see. Then you prove these other two properties, but that will just be formal verification, right? D1 and D2 have have all these properties, then this also has those properties. That's a formal verification. But you need to know what this even means. What this means, D1, D2. And D1, D2 is actually not in this TPM. That is why we need to take the Lie bracket. Right. But how do you interpret D1, D2? Okay. Because you see, I mean, a priori D1, D2 is not a function from C1 to CM to R. If you just interpret it naively. Because if you take a function f, you see my point, right? If you take a function f, right, then this thing becomes a number, then you can't apply this to this, right? But that's not how we interpret it. What we do is we interpret this as a C infinity function, as a continuous function, right? Because it is taking now the points are changing. Okay, so it's taking a point P, right? And at that point P, oh, okay, is taking a point P and returning and then is taking d2 of f at P. So that's a number. Okay, so this thing becomes a continuous function. right? And then you apply d1 on that. Okay, so that is what is happening. But there is a slight problem. There is a small problem, but maybe we can talk about it later. The problem is that then you want d2 to be defined not just at p but at other points also. Okay, because you're going to take d2 not just at p, right? So that is a separate problem, and then we have to say that you don't take Lie brackets of in the tangent space. Hmm. No, actually you can take it, but I'll not talk about, let's not talk about it right now. Okay, let's understand that it can be done. And then you just formally verify that these two, that this is also, and you also try to show that these two definitions are maybe same. Okay, because like one thing is clear, right? I mean, if you take f, if you take a gamma, if you take a curve gamma, how do you get a derivation? How do you get a d? Well, you to get a d like this, you take gamma, then you just take for any f, you take f gamma and you take d dt, right? So f going to this becomes a derivation. Is that right? Right? So you had a f, so you have a f, right? You have a f which is a continuous function, right? Gamma is fixed. So using gamma, you want to get a derivation, right? So how do you do that? You just take now the derivation I'm defining like this. Take f, decompose with gamma, and then you take d dt of that. So f goes to this number. Okay, and that becomes a derivation because I've told you a way to go from f to a number, right? By using a gamma. So it gets it, and then you can verify this property. It's a very natural definition. This is how you actually define directional derivatives by taking a by taking a curve whose derivative is equal to that vector, so on. So you can prove the equivalence. Okay. So these are the things, and yeah, let's stop here, I suppose, because yeah. So, but you should also think about how to define this. Okay, I mean how to calculate this. At least calculate it at the identity. Is that right? At least calculate it at the identity and see. I mean, you can use this to actually calculate it. Yeah, at zero maybe you can calculate it. So yeah, and these things we did not do, but maybe we can. Maybe you should calculate these things and tell me. Yeah. Hmm. So this is the function from MNR to MNR. So calculate the derivative of this, right? You can do that. I mean, the question can be asked at least. Yes. So see, what you are doing here, what you are doing here is is basically, so if you have that f, right? That's right here. So you have that f. So you take df, right? You take df. Let's say df. So what is df? So df at a point at some matrix B. What is it? It is a function from MNR to MNR, right? So you want to compute this. This is a linear function from MNR to MNR. You want to compute this. So if you take B to be the zero matrix, and then you ask what is this uh, linear functional at A? Yeah, where does it take A to? Then uh, It is just a, because actually this is what you have actually calculated. You see, what you have calculated is basically this, right? Because yeah, right? If you think about the definitions, you will see it will become clear. So what you have calculated is a very special case of the total derivative. Okay, so that's why you should now calculate the total derivative. Right? That's the point. Yeah. Uh, yes. It's a yeah. It's a cool thing. Yeah. And yeah. Okay. We try to do it and then see. Okay. Okay. Then for today we are meeting tomorrow. So if you are joining, then you can just join if you're there. Yeah. No, 8 p.m.